we will move on to the next speaker, who is Patrick Meade, will tell us about physics opportunities at future colliders. Patrick.
Hi, thank you. So bring this up.
Could you go ahead and share your slides? Okay, I'll give a warning, a 5-minute warning after 25 minutes.
Okay, sounds good. Let me just bring up the chat quickly. Okay. So first of all, thank you to the organizers for inviting me. Tao gave me this, let's call it a generic title of Physics Opportunities at Future Colliders. And he said I could replace it with a juicier title if I wanted. So I played around with it a little bit, but really I couldn't come up with anything. An alternative title is just a bunch of thoughts I've been having since the snowmass process has been sparking my imagination a bit. So this is based on work with lots of people thinking about BSM context and also thinking about more the forward direction with muon colliders I've been thinking about lately. But since that's a really boring title and no one would have shown up for this particular title, we'll keep the original title, Physics Opportunities at Future Colliders. Now, of course, some generic title like Physics Opportunities at Future Colliders, this could be a very standard talk, okay? In the last few years, we've had an enormous amount of work thinking about future colliders. A lot of this started at the last snowmass and P5 process almost a decade ago. But just recently, we've had the European strategy update that came out last year and snowmass, which is currently in the process. So there's been an enormous amount of effort thinking about future colliders and what we can get at them. This is just a random figure grabbed from the European strategy update showing, for instance, how the standard proposals like FCC or ILC or CLIC or CPC can do for the triple Higgs coupling. Okay. So this could be a very standard talk. Of course, since we've been doing this so much and we've all been stuck on Zoom for over a year now, I don't want it to be exactly like that. Okay, so you've all heard future collider talks, probably from people who give them much better than me. So what I want to do to start off is maybe think a little bit differently. And I want to analyze from my idiosyncratic perspective, first, what are the physics opportunities we're really interested in? Okay, so what kinds of opportunities are out there? And since Tao didn't give me any explicit directions on this, I also want to talk a little bit about today, what are the options? Okay, we're very used to this perspective of being told, well, there's the ILC, there's CLIC, there's FCC, there's CPC, SPPC, but really, is that all there is? And what other interplay of these two ideas can get us to possibly other ideas, thinking about the future of our field? So an obvious question when you're trying to think about physics opportunities in future colliders is what leads? Is it the physics opportunities that lead or the future colliders that lead? Now, of course, you would like the physics opportunities in some sense to lead, but in the field of high energy physics, these projects are becoming so incredibly large, and we really are always at the bleeding edge of technology, and it would be presumptuous for theorists just to be proposing new colliders all the time. So we're typically going in the other direction, where there are a number of proposals out there for future colliders, and we're typically then working out what physics opportunities these give us. Okay, we're just limited by the fact of technology, cost, etc. And that gives us the standard picture on that former slide from the European strategy update that I gave, where we take the standard proposals that are out there and we just work out the physics reach, not even necessarily the physics opportunities. We're all very familiar with the kinds of things that we're looking at. And we, for instance, get a bound on the kappa parameters for the Higgs. Or if you take your favorite model, you can get a bound on the mass of the various particles based on what particular collider options. So we're very familiar, especially in the last decade or so, of going this direction. okay? And because of that, we understand why these various proposals came about, okay? There's some basic physics input to what sorts of colliders that are typically talked about for future colliders. And essentially what we're used to based on that list is there are effectively two types of options that get discussed most in our community, okay? We can either build a new collider out of electrons, which we've done many times before, or we can build a new collider that collides protons, which we've also done before. And these typically fall into various different types of them. For instance, for electrons colliding E plus E minus, there are two different flavors of this. We can either create linear colliders like the proposed ILC or CLIC, or we can make circular colliders like CEPC or FCCEE, okay? Now, of course, there's pros and cons to every type of future collider options. Electrons are very interesting from the perspective that they're fundamental particles and they give us kind of cleaner events and let us do precision physics, which is the kind of analog of what the LEP program was before the LHC, okay? But of course, they're also effectively energy limited because in the case of circular colliders, we lose so much through synchrotron radiation. So you can't just effectively keep raising the energy there. Or, well, linear colliders, we can try to keep raising the energy more and more, but then we run into effective constraints with power consumption and Beamstrahlung. So this is the one side of it. We normally think of these as the precision future colliders. The other option is to use a heavier particle so that we can accelerate it to higher energies in a circular machine without losing as much to synchrotron radiation. But in this case, we know that we're very familiar with this from the LHC, even though we can attain higher energies with proton-proton colliders or PP bar colliders. These give us essentially dirtier events because we're not colliding fundamental particles. We're colliding the constituents inside the proton, the quarks and gluons. So these give us dirtier events. And that's why, not surprisingly, we have this basic picture of a series of electron and proton colliders to kind of set the table for what the future colliders that came out of the last snowmass were and what we've been thinking about for the future. But what I want to also add is that we're also thinking to the future and trying to kind of have this confluence of all the knowledge of both theorists, experimentalists, accelerator physicists, and a lot of interest that's come about lately is the dear old muon. Okay. Now I'll talk about this more a little bit later, but it has the potential to be the best of both worlds in the sense that we're colliding an elementary particle, so we get to get essentially the most bang for the buck, but at the same time, it's a lot heavier than the electron, so we have the ability to accelerate to higher energy. So in principle, muon colliders are another option, and they could provide the best of both worlds. They could kind of bridge this energy precision dichotomy that we've always been thinking about for the last many decades. But of course, the drawback is we've never actually built a muon collider before, so this is obviously on the bleeding edge. Now, maybe we'll find out through further studies, and there's a lot of work going on through snowmass that we can think of the muon colliders, one collider rule them all. But for now, I'm not going to kind of go in any particular direction. I'm just going to say, well, maybe we could take this normal standard talk and we could update it to, for instance, add a muon collider and ask about the physics reach. But I also think it's interesting for the sake of our field and thinking about what possible physics targets we're going to get to, it's also important to keep an open mind, okay? People are thinking about new technologies all the time and versions of colliders that can be accomplished. For instance, another option is a gamma-gamma collider, for instance, at high energies. So there's a long list of various potential opportunities for future colliders, and we'd like to understand what their physics reach is. But again, we've done this many times. Many of you in the audience are involved in this, have written papers on this. I'd like to go in a slightly different direction for this talk. And what I'd like to do, because I'm a theorist and I don't have to actually build a collider, I'd like to think about physics opportunities and do the slightly more presumptuous thing of saying, what are the physics opportunities and what does that imply for future colliders? Okay, instead of going the other direction, which we're all very used to in our day-to-day jobs as phenomenologists. Now, of course, this is thinking a little bit outside the box, and this New Yorker cartoon, never ever think outside the box, always comes to mind for me when you try to push in a different direction. But what I really want to emphasize is that maybe there are particular physics reach goals that are motivated by our current understanding of theory and the input from all of the many experiments that have been running for the many decades previously in high energy physics that could potentially single out some of these options, okay? And another important part of this is, are there quantitative differences that come from thinking about these physics reach goals that would lead to a qualitative difference in our understanding of our universe? And in which case, maybe that quantitative difference tells us that maybe the options we're listing here are not yet on the table. Maybe we really have to think more about R&D for future colliders to ever really reach some of these qualitative differences about our universe. So my aim in this talk is not going to be a particular conclusion. Okay? Everybody has their favorite idea for what the next future collider should be, or what you should think for pie in the sky 100 years from now. But I'm going to try to give you some food for thought and an incomplete BSM wish list to, in some sense, motivate future studies if people are interested along these lines. So if we're going in this direction of physics opportunities to future colliders, okay, we can throw a lot of different ideas about theoretical physics and our understanding of the world. For instance, we just heard a nice talk about like overlap with what does string theory tell us for crazy possibilities that might be testable, or new particles that might be lying around. That's another way to say that. So if I was trying to do this, I could go the fancier route, but we already know what the underlying idea is. The simplest version of this is obvious, okay? Highest energy possible, okay? So I'll go into some more theory, but starting from this basic idea of the highest energy possible, we all know this depending on whatever subfield of high energy physics you are, okay? We all have this picture that by going to higher energies, we're able to explore new territory in terms of length scales. And you don't need any fancy theory arguments for this. The standard thing you see in accelerator talk, you see uncertainty relationship and higher energy, shorter distances, blah, blah, blah. Or you see these very beautiful pictures made by the DOE and other components, funding organizations that at the same time, not only are we just exploring the undiscovered country by going to higher energies, we also have this picture given to us by the picture of cosmology of the Big Bang, that by going to higher and higher energies, this is really also our window into the early universe, okay? Because we always had this competing effect via cosmology that we know the CMB formation, okay, that likes to screen out what we're looking for before. And unless we have probes that are imprinting themselves, for instance, from things that were active right around the time of inflation, it's very hard to go any earlier in the universe without some direct probe. So we have the standard argument for we just would like the highest energy collider. You don't need any deep theory to get to that. And the nice thing about this is, even though you can, we're on webinar, so I can't see you laughing, there's an ultimate goal, of course, though. We know what the ultimate goal for future colliders is. We would like to test directly with experiments up to the Planck scale, okay? Now, there might be things obviously coming in before there, but that really is kind of this ceiling where we don't have to just say we're always going to be going forwards. We'd like to cover from where we are to this. And of course, the question is, how close can we get? Now, colliders used to have this beautiful version of Moore's law, okay? And this came under the name of Livingston's law. And that was the statement that there's roughly a doubling of energy every 6 years or so. And that's this trajectory here, okay? And of course, if this doubling kept going, even 6 years, the doubling time's a little bit longer than Moore's law. This allowed us to speculate quite a bit earlier in our field as this perfect law seemed to be being followed. And for instance, this allowed Fermi to speculate around 1954 when he was stepping down as the APS president. And this is more a lark, not an actual proposal. But he was able to take this Livingston's law and speculate 50 years or so into the future. And this is the so-called globotron that Fermi proposed, which was a 5,000 TeV center of mass collider. The only thing, of course, the drawback was you needed to put the collider ring orbiting the Earth, okay? So it's a crazy idea, sure, but at the same time, we have seen progress in accelerator physics at the same time as we have progress in all fields. So the starting point here, we could say, is why not imagine, for instance, a PeV collider? Maybe I won't say a 5 PeV collider, but let's dream big for a second. And where can we get? This is the only thing I can say I have in common with Fermi other than the field that I'm going to be crazy and dream about PeV scale colliders. Now, of course, you could say, well, if we're not building a collider around the Earth, it's probably out of reach anytime soon. And more specifically, why is it becoming out of reach? And why do we have this sense in our field that we're not taking these gigantic steps anymore? Well, that's because this so-called Livingston line is already broken. So taking this figure from this book, this shows that, for instance, while we're following this Livingston line all the way roughly up until the Tevatron, we're starting to deviate more and more. What we see here is that the LHC has deviated quite a bit from this. And that's not the sense that the accelerator physicists are doing anything wrong. This is just the fact that at the bleeding edge of technology, expanding things that we know how to do, there's a lot of other influences that are coming in. And there's some sort of reality check that we're not going to be driving a collider to the Planck scale, let alone the PeV scale might be a little bit hard right now. So if we go to our first entry for a reality check on Google, the first entry that showed up for this is some sort of funding thing from Texas. And so let's kind of view this as, will you be able to afford the collider you want? Okay, so we need to define what that collider is and will we be able to afford it. This is a complete accident that Google showed Texas as the first thing when I typed in reality check, and there's obviously no correlation to the SSC, but it's also a very amusing fact that if the SSC had been built and not canceled, and we go around here or so, and then we go up to around here, and we would have been continuing this doubling every 6 years or so, okay? So we've already seen this law breaking, but we had a chance of still staying on it. We're not crazy separated from this, but there's of course many competing factors. Cost is number one in some people's mind, but these projects also take a long time to realize depending on the how ready the technology is, and there is technological limitations to all of these various options. And the thing that also sometimes gets lost into why these limitations come about so far is it's also not just an energy race. I could tell you to build me a order Planck collider, but if I have no events, that's of no use to me. We know that the cross sections, if I'm trying to produce new BSM particles from standard model particles that I'm colliding, are dropping with the center of mass energy squared. And if I want to have events, well, it's the cross section times luminosity. So if I don't want to just have the number of events scaling away as they go to higher energies, we also need the luminosity significantly scaling with energy, okay? I'd ideally scale with the energy squared. So if we're going decades in energy, we need to also keep in mind there's going to be constraints on how much luminosity that we need. So there's many competing factors that come along to thinking about these future colliders, even from this basic idea that energy is the best and that's the thing that we want to go for. And at the first SNOMAS in 1982, they were even compelled to write this up. Okay, we all know these things, but here's a SNOMAS report from 1982. So ideally, everything's driven by physics, but of course, there's a lot of other things. So if we don't make it here to M. Planck as of yet, what I want to stress for the rest of the time is, are there some interesting signposts along the way? Okay, is the PeV scale the scale that we're interested in? Is 100 TeV like FCC and SPBC the scale we're interested in? And are there some existing collider options that are more exciting than others, or do we need to think about other colliders that have not even been put down on pen and paper, so to speak? So this leads me to this idea of going from physics opportunities to future colliders and what they imply. Okay, and this is just some brainstorming. There's no hard rules that come out of this, but I'm going to talk briefly about three main categories that have a ton of overlap between them, but that hopefully, the idea of this is that by looking at the physics that we know from experiment and theory, they're going to lead us to some targets that I'll call euphemistically this BSM wish list, and analog to what we had long ago before the LHC was the NLO wish list, which was experiments telling theorists what they need to calculate. I'm going to go the opposite direction. As a theorist, I'm going to tell experimentalists and accelerator physicists what I'd really love them to build. Okay, even though we might not know how to do it. Now, of course, you can say, well, this is all just kind of silly, and maybe your BSM motivations point to ridiculous scales, blah, 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 or maybe no other experiments see anything new. So you could be the standard old curmudgeon. Okay, the standard model is all there is, and you're not going to change my mind. But the nice thing about this kind of programming for a BSM wish list is even if you're this much of a curmudgeon who thinks that it's just the standard model and maybe nothing else until the Planck scale, the nice thing is this first one about completing the standard model and measuring the Higgs, you can't curmudgeon your way out of this, okay? If you believe it's all the standard model is everything there, you damn sure better complete the standard model in your measurements. So we often act as if the standard model is complete. But the thing that sometimes doesn't get stressed enough, I think, of our community talking to, for instance, other physics communities at the least, is that we still don't stress that even though we've found the Higgs-like particle, we still haven't measured many of the couplings, even at an order 1 precision, or even observed some of the couplings that the Higgs is supposed to have. So there's an enormous number of questions associated with the Higgs. For instance, why on earth do we have electroweak symmetry breaking? Is it just flipping this minus sign in the Higgs potential? Who ordered that? Okay. Questions that come directly along with having a spin zero particle are naturalness. What is the Higgs potential? The Higgs is responsible for all flavor physics in the standard model. So is it true that it's actually doing its job? How does the Higgs play its role in the early universe? Now, immediately you should say, well, aren't the Higgs factories supposed to do this? Haven't we already set out this program? You could, for instance, take the European strategy update and you could say, well, let's do a kappa fit to the Higgs. How does all the couplings to the Higgs vary? And we could look at the precisions. And you could say, okay, well, compared to the LHC, lots of future options do much better than the LHC. And I've even thrown in a 10 TeV muon collider just for kicks and giggles. But one of the real questions when we stare at one of these tables are, what are the biggest missing pieces still after the LHC? Okay, we see things are improving, but can we finish off the standard model? How do we do this? And what's left? So in particular, two of the biggest pieces that are going to be missing are testing the Higgs self-couplings that we know should be there for fundamental scalar in a different way than all of the particles we've seen so far. And moreover, we've done great about measuring the Higgs couplings to very heavy particles, but for very light particles, we are still just kind of scratching the surface at best with the LHC. So these are two big directions, but of course, we have to ask, how well do we need to measure these various new things to complete the standard model? And we've been developing this picture over the last decade or so. For some of these things, we think we have a very good idea. So for instance, the Higgs self-couplings, we know it can be related to a first order electroweak phase transition in the early universe or electroweak baryogenesis. And we've been talking a lot about how there's kind of two differences in cosmology we can separate. You should have a shift in the triple Higgs coupling of order, let's say 10% or more, if you have a strong first order phase transition at the electroweak scale. Or if it's just the standard model and it looks like a crossover transition, this should give you no deviation. Okay, so the lore, of course, it's easy to distinguish these. But what I want to emphasize in terms of setting up a BSM wish list is that theory marches on, and we need to be careful about kind of what our targets are. So as an example of this, something that was done in collaboration with Higher Money and a number of other groups after us, we now realize that the Higgs potential doesn't have to have the standard picture that, for instance, you take out of a cosmology textbook that says the electroweak symmetries are stored in the early universe. It could actually, in the early universe, be more and more not restored, or you could delay it and restore it at a much higher temperature. And there's three very qualitatively different histories of the universe, and in principle, it needs a delta lambda much less than 1% to distinguish it, which is well beyond that very first slide I showed on the triple Higgs coupling.
Patrick, sorry to interrupt. It's 5 more minutes.
Yep, sure, no problem.
Thank you.
Higgs self-couplings, more generally, instead of thinking about this for the phase transition, if you just thought about a new particle coupling to Higgs and having some quartic interaction, if you just take the only quartic we know, which is the standard model Higgs one, what you get is a shift in the triple Higgs coupling of order 10 to the minus 3, not order 50% or 10% like we talk about. Another interesting one is the first and second generation Yukawa, okay? Now, of course, this is very difficult to measure. If I think about the ILC or FCCE, et cetera, if I think about trying to measure the down quark Yukawa, first off, just the inherent difficulty is ridiculous. But at the same time, we're having order 1 events, even if I could tag these events magically. But there are models that change this. So it's important to think about our benchmarks going forwards. So switching gears, BSM motivations. We have lots of open questions about the standard model that we'd like to try to answer. And a lot of these will remain, even how well the LHC will worked. And we're always coming up with new possibilities too. So I'll just take a couple of these very quickly. Naturalness, of course, it can fit in with the Higgs, but at the same time, it really is kind of one of these tenets for BSM physics. And although it's not often talked about as much, the report of its death was an exaggeration, because since we found the Higgs, it's even more an alive problem. And what's dead from the LHC is in some sense the most natural elegant solutions. So we in some sense have two options. We can be a little less natural but simple, like Susie at a higher scale, or we can be slightly less simple but possibly more natural from that perspective, like for instance, twin Higgs or neutral naturalness. So for instance, we see here, if we take some of the simplest options, take mini split supersymmetry, and let's say you want to also think about dark matter. So we know at 3 TeV is a thermal relic. This implies roughly that your gluino is going to be at 30 TeV, and you see, for instance, the FCCHH reach for gluinos, you see this is only 17 TeV. So there's a lot of room in our minds for a BSM wish list. Or you take a composite Higgs, so stealing the slide from Raman, the simplest models, but slightly less natural, really kind of top out realistically with new states in the 10 to 100 TeV scale. And if you think about neutral naturalness as another option, going the other direction, where you have, in some sense, 2 loop factors to get to standard model partner particles, unlike SUSY or composite Higgs, there, this naturally sets a scale for 20 TeV particles that we'd like to go out to directly test this. So this was just another set of examples of BSM motivations providing kind of a higher scale. And it's not just trying to move the scale beyond the LHC, it's just trying to take the input, understand what the theory is, and what does it tell us about what there could be out there. The last one I'll just briefly go through is this idea of complementarity with other experiments. So there's a lot of other ways to test physics beyond the standard model, beyond just the energy frontier and big colliders. There's many approaches to getting to this, through rare processes or using cosmology. But the problem always is, if we get indirect hints of something, okay, we really want to lay our hands on it and understand, is it truly pointing to some particular new physics? So we need to think about this in the context of what are existing hints now and what are planned experiments coming up. And we better start thinking in terms of the energy of colliders, how to actually get there in terms of a higher scale. So current complementarity, G-2, for instance, points to possibly a 30 TeV muon collider. Gravitational waves, we now have this beautiful new probe that can go back earlier in the universe. But if we see some signal, are we going to really believe it's new BSM physics without some complementary measurements directly? And so, for instance, current scales from LIGO and LISA point us to these astronomical scales, and the assumptions we make are important, but it's a very promising direction for complementarity. And the last one I'll just briefly show is this idea of, for instance, the EDM has been something that's been marching forwards. We're going to gain orders of magnitude on this. If we saw deviations, what does it imply? So, for instance, taking some basic assumptions of this, it really points, for instance, for EDMs to astronomical scales if we're seeing it at the limit of these experiments. So I'll just flash an incomplete BSM wish list, okay? There's many possibilities for BSM physics, and it points to scales that are astronomical precisions that are needed. So the question is, how do you flip this to ultimate colliders? So I'll just flash this very briefly, but what I want to emphasize is most all of this wish list needs energy. Motivated targets that we know about right now extend from tens of TeV to the PeV scale based on future experiments coming up. There are only really two realistic options for this, muon colliders or proton colliders. However, there is a very important option to completing the standard model and testing first and second generation physics. And this is using a low energy lepton collider with the highest luminosity possible, plus detectors that can do great particle idea. So existing things or even newer ideas are out there for acceleration. Maybe this all sounds crazy to dream, like this is a crazy theorist just saying, build us a PeV collider, but there are other physicists out there in the accelerator community dreaming these dreams. So this is an example of a collider in the sea, a vision for how you get to the 500 TeV scale with future colliders. I'm even more excited by muons. I'm running out of time, so I'm just going to flash this. But for instance, 10 TeV muon colliders really provide us an interesting reach. And thinking to the future, a 10 TeV muon collider on a Fermilab campus, this is a slide from accelerator physicists. And even crazier, we can get to the PeV scale. This is Vladimir Shiltsev's review showing here's an option using this even crazier than plasma wake fields, using these crystal accelerations to go to the PeV scale with muons. So there are physics opportunities and potential paths for future colliders. What's the best next collider? I think from our epidemiologist friends in the pandemic, obviously the answer is the first collider the community rallies around and is funded. But I want to leave you with this idea of don't forget to dream bigger. Since PHENO 2021 is at Pitt, we can use the Cathedral of Learning as motivation. Obviously, building this building in the early 20th century was a crazy idea, and the community was scared by it in terms of this big thing sticking up. And they'll obviously claim, is it too expensive? But I just want to end with this idea that science funding isn't a zero-sum game. Look at the trajectory of R&D over these various agencies and see if you notice, for instance, the SSC cancellation. This didn't suddenly result in money flooding to all the other fields from the government. You can zoom in this even more in DOE and look at these slides later on when I upload them to Indico. But science isn't a zero-sum game, okay? We have to make the case. And science isn't political. You look at the most recent things in the US, the Endless Frontier Act, at least the old name of this is one of the most bipartisan things coming out of the US government, okay? So we live with the tragedy of the SSC, but remember, we have the ability to make the case. The P5 charge last time left an unconstrained budget, so it's up to us to make the case for the world. And as a historical perspective, going back to the very first snowmass, they were talking about a 40 TeV PP collider and a 2 TeV EE collider. We were thinking about things similar to the current proposals 40 years ago, but a lot of physics has changed in between. So let's dream bigger together for the future, and I'll end there. So thanks.
Thank you very much, Patrick, for a very nice and forward-looking talk. We do have time for one or two questions. I see one in the Q&A, so let me begin with this. Do you view collider R&D as a necessary step so we can make an informed decision when or if we see hints of new physics? In the absence of any of these complementary hints, what do you view as the most compelling case? Example, Higgs factory with EE, LINAC, or muon collider?
Yeah, I think collider R&D is an enormously important thing. I mean, if we think about the budgets first, in terms of thinking about the money that we spend with the LHC and elsewhere, if we could increase our funding for collider R&D, it in some sense would open the doors to many of these things. And in the absence of a specific scale we wanted to go after, if we were to kind of think about Higgs physics, I think there's a real interesting option, because even just completing the standard model, we have kind of this dichotomy set up by trying to measure the first and second generation and trying to measure the Higgs self-interactions. If we want to go after those, we really need energy because you get a big enough cross-section to measure the Higgs self-interactions. And at the same time, we really need precision to get these first and second generations. So I honestly would say, as my personal view, okay, this doesn't mean anything to the field, I think a 10 TeV muon collider is a very interesting option as kind of an all-in-one collider option. But at the same time, I really don't think that's going to give us necessarily the precision we need to fully complete the standard model with the first and second generation couplings. So I am very intrigued by seeing how much a Higgs factory, for instance, at the ZH threshold can get to as much luminosity as possible and then augmented by a 10 TeV or any kind of very high energy machine. So that's just one take on this, but I can obviously be moved on. My opinion has changed over the last year, and everyone else probably has their own opinion too.
Thank you. Let me ask a question. About 25 years ago or so, there was a significant interest in muon colliders. And one technical problem that was faced at that time, I recall, was the neutrino radiation. Is that still an issue, or
so? I mean, obviously, anytime you talk about a muon collider and you have straight sections of the collider, neutrino radiation is something that you have to mitigate. As part of SNOMES, there's this muon collider forum that we've been running, and the last meeting we actually had was on like what are the typical showstoppers for muon colliders. And the sense from both the International Muon Collider Collaboration, of which there is one now based through CERN, and the US community, most of the people working at Fermilab, is that neutrino radiation is something that can be mitigated. It's not just kind of like you just do it easily, but there are a number of ideas in terms of, they even have ideas of not only kind of, can you put this at depth in terms of how you also design the ring architecture, but now there's ideas to, for instance, move the beam mechanically so that you're not always radiating in the exact same direction. And the idea of the muon collaboration, the one based at CERN, is they really think they have the ability to get the radiation below the LHC levels, so you wouldn't even need to petition anything special to get a muon collider built. But there's obviously other technical hurdles too, but at least that's the answer for that one.
All right, thank you very much. And